Hello, can everyone hear me? Everyone okay at the back there? Fantastic. Okay, so I'm going to be here talking about static analysis, both for code and for infrastructure, which is somewhere you don't often see it. To give a bit of background to this talk, the aim here is software developers make mistakes. We all make them. Mistakes means bugs. Bugs means security vulnerabilities. The overall goal is fewer bugs. I'm sure some of you recognise some of the logos down the bottom there. Over the last couple of years, we've had some fairly catastrophic bugs in a variety of things. Shell shock was one of the worst. These happen because someone somewhere screwed up. So we're here to look at how we can fix that. Who am I? I'm Nick Jones. I work for MWR Info Security as a security consultant. I work on web application infrastructure security usually. Prior to this, I was a software developer doing embedded systems development, so I have some idea of both sides of the coin here, which has helped out over the years. So, brief overview of what we'll be covering. Why do we need static analysis? What does that give us? How do analyzers actually work? Give you a bit of the background so you can understand what these things are doing when they're running. A look at a few of the different applications of them, what the kind of bugs you can catch with them, and talk a bit about how that fits into DevSecOps as a whole and how that works. So, start off with why do we need static code analysis? So, fundamentally, the first question you need to answer is how do we actually find bugs? Two schools of thought on this, or two different approaches. You have static analysis, or SAST, as you'll hear Gartner calling it. Take an application, analyze it in some fashion without executing it. Typically this is done by code review if you have access to the source code. If you don't, then either reverse engineering or some kind of binary analysis. The other approach is dynamic analysis, so you run the application, you monitor it as it's running, you interact with it in some fashion or another with the aim of finding bugs. So fuzzing, tampering, functional testing, the traditional penetration tests and so on, that all falls under dynamic analysis. Funnily enough, given the talk title, we're going to be focusing on static analysis. Here, we're looking mainly at code review. I understand there's quite a few vendors that do various binary static analysis tools. I don't know a huge amount about those. Please don't answer me questions on them later. So how do we do code review? Two approaches. Manual, give it to someone who understands the code. Expect them to find some bugs for you. There's a lot of very smart people in the security industry, a lot of them with a lot of experience finding obscure and esoteric bugs in software. That typically works quite well. The other option is to do it in an automated fashion, pass your code to a tool, the tool will parse the code, hunt for some issues that it understands. The tool has some understanding of how the code operates, and you hunt classes of bugs based on that. In terms of doing manual code review, a couple of examples. Really basic buffer overflow here. No one's checking how much stuff is going into the buffer you've got there, so there's a potential for the overflow in the printf statement. And likewise, if we've got any Android devs in the audience, having JavaScript enabled on your Android web views generally doesn't end terribly well. Nice and easy to spot when you've got a couple of lines on the screen. When you're looking at large code bases, that starts getting very complicated and very expensive. I pulled some numbers on the sort of sizes of some of the more famous code bases these days. 86 million lines of code for Mac OS X was one of the bigger, but even the new Joint Strike Fighter's got about 24, 25 million lines. There's an awful lot there to try and analyze in a manual fashion. And Steve McConnell, who wrote Code Complete, reckons somewhere in the region of 10 to 20 defects of some sort, not security bugs specifically, but bugs of some class or another, per 1,000 lines of code, which works out with some pretty staggering numbers. 1.25 million for Mac OS X apparently, but even in what is supposedly a brand spanking new fighter jet, you're looking at 350,000 bugs of some sort or another. That's an awful lot of bugs, and expecting people to find that manually is probably too much. So instead, we do static code analysis. Automated searching of source code for issues in the context of source code analysis. Higher upfront cost generally if you're developing the tooling from scratch, but once you've got it set up, built with a decent rule set, it's essentially free security. You pass your code through the tool, it gives you some results, and will catch quite a few things for you. A lot of the sort of the low-hanging fruit will automatically be picked up by it, and your devs can fix it nice and early on in the development lifecycle. So, to understand a bit about how these tools work, let's have a look at the some of the theory behind it. So for those of you who did computer science degrees, I apologize, you've probably seen a bunch of this before. And for everyone else, I'm trying to compress a semester or so of compiler theory down into 5 minutes. So this is a bit of a whistle-stop tour. But nonetheless, fundamentally, programming languages are essentially just a set of strings of symbols that have been defined by some sort of rule set. We call that rule set a grammar. You have different grammars for different types of languages, depending on the rules for that language specifically. There's a guy called Noam Chomsky, who some of you will no doubt have heard of, defined a hierarchy of languages. Each language is a subset of another, and as you get further down the list there, the grammars that define them are stricter, which also means it's easier to implement faster parsers for them. Most programming languages roughly fall under context-free, so that's what we'll be talking about here for the most part. A context-free language is anything that can be parsed by a context-free grammar, which we'll look at exactly what that means in a second when we get down to how the parsers for that work. But we're looking at that, like I say, because for the most part, programming languages are context-free. This is why, if any of you have ever tried to parse programming languages with regular expressions, doesn't generally tend to end too well. And there are limitations around what most regular expressions are capable of doing, which makes this quite nasty. I'm also saying mostly context-free because things like C++, with all its templates and macros, throws all that off completely. But context-free grammars get implemented as a push-down automata, which is essentially a finite state machine, but with a stack bolted on the side of it that you can push and pop from. Allows you to decide transitions within your state machine based either on what's coming in from the tape, what's on the stack, or both. So that's essentially how parsers for most programming languages function. So you define a grammar, that is then implemented as a state machine with a stack, that's used to convert the source code you pass into it into some kind of hierarchical data structure. Usually an abstract syntax tree is what you're working with when you're doing static analysis. An abstract syntax tree is a tree of tokens, so different bits of a piece of source code with information attached as to what they are, whether they're function calls, variables, so on and so forth. Parsers typically break down into two separate stages. Alexa takes the source code as it is, just a text file with no meaning, and splits that into tokens, identifiable pieces of a programming language, be it, as I say, a function call, a variable, line terminators, so on and so forth. And then once the tokenization process has been completed, a parser then walks that and gains some understanding of actually what each of these tokens do. As an example of Alexa, so we've got here someone's doing some debug output, and we've got some printfs to print some code. So Alexa, after you've run it, will pick out that we've got function calls, some variables, line terminators, the brackets to define a code block, and so on. And then when that gets parsed into the parser, it finds the if statement, works out that we have an if statement there. Bracket realizes we have a code block. From there, you then pick up the printfs and close the code block off again. But this gives you a hierarchical understanding of the program that you're looking at, which means you then have a tree you can walk and gather information about. So now that we've got an abstract syntax tree, what does that actually buy us? So you can search the AST at a basic level for things like calls to functions you know you don't want, debug gods if they should be there, maybe they're not, maybe you're outputting data to locations that you don't want it to in a production environment, log files, so on. Questionable imports potentially, depending on the parsers you're using, and so on and so forth. You can do this with regular expressions, a lot of people do. Having an understanding of that code structure that the abstract syntax tree gives you means you get far fewer false positives as a result. But the real power of having an abstract syntax tree comes in from the control flow graphs that we can build off it and the various types of analysis we can do from there. So let's take a look at what a control flow graph is. A representation, using graph notation, of all the paths that may be traversed through a given piece of code as the analyzer has scanned. So each basic block within the control flow graph is defined as a set of statements with a jump target at the start and a jump at the end. So for instance, if you have an if statement with an else clause as well, your three basic blocks there are the if statement itself, the contents of the if block and the contents of the else block, as defined by the appropriate jumps either side. Some of you might have come across it for use as compiler optimization. It's a good way of filtering out unreachable dead code, detection of infinite loops, optimizing arithmetic, that kind of thing. To give you an example of a few, the one on the far left there, A is a very basic if then else block. B is a while loop. You have a loop going on with a jump condition that breaks you out of it. C is a loop with a break clause in. D is a loop with 2 entry points. If someone's got some nasty go-tos in their code still and you're jumping into it that way, you can end up with some quite nasty control flow graphs as a result. But having an understanding of that allows us to do quite a few fun things with it. So now that we can trace execution without actually executing the program, we can do a number of different types of analysis. The core ones we're going to focus on here are taint analysis and pointer tracking. So, taint analysis. Look for sinks of data. If you have a web application that's querying a database, the point at which the data goes into the database query function is an example of that. When you see some input being passed into a function like that, you can then walk back up your control flow graph to see where this data came in. It's possible that the data sanitization was performed right at the beginning. If you're scanning with regular expressions or you're just reading it through yourself, it can often be quite difficult to track back exactly where that happened. But with the power of control flow graphs, you can do that in a fairly automated fashion quite easily. So as an example of what we can do with taint analysis, some terrible PHP I threw together, you can see we've got a query happening down the bottom where someone is just passing in strings into a query there. That's not great, but we don't automatically know if there's a vulnerability there looking purely at that function call down the bottom there. So what we can do is track back up to where the 2 variables being passed into it came from. Here they're being passed into this login query function. Okay, where was that called? Back up again. We have them being passed into the function call there, and they came in turn from the function call for that function. And right back up the top there, we have unsanitized user input being passed in. We've not found any sanitization happening as part of that process, so we can then say that there is an SQL injection vulnerability there. Looking at pointer tracking, when you're walking the graph, we can track creation and destruction of pointers. We can track where memory is allocated, where it's deallocated, and as a result of that, you can then follow the control flow graphs through and identify where you're double freeing a pointer or you're referencing memory that's been deallocated already, so on and so forth. So as an example here, we allocate some things, we create a pointer. If we reach an error condition, then we should free this pointer. If, however, we are also in debug mode, then maybe we want to print some stuff out. But because that's happening after we've freed it, we get a memory corruption issue here. The fundamental problem, though, is that in many cases, you may not spot something like this the first few times it runs, because let's say we're not in debug mode, that's never going to actually crash. But walking through it, we can see, having followed our control flow graph, we've got a malloc here. Okay, that's fine, we'll register that. We then also notice that there's a free that happens here. Okay, that's fine. Let's see if this pointer is then used anywhere else. And lo and behold, we spot down the bottom that it is also actually used here, and so as a result, there are certain conditions that can cause a memory corruption. You can use it to find null pointers, used after frees, dangling pointers, a variety of issues like this. Now, as we're at a DevSecOps conference, let's take a look at what we can do with it in this context. Static analysis in an SDLC is no doubt something that quite a few of you are using already. Catch a lot of the issues before it gets to the stage where penetration testers are looking at your application. And if you've got a couple of smart devs who can build this kind of tooling or who can work with existing tools to develop rule sets for your application, and then you can use that within the context of the rest of your development team without any real additional required effort on their part. You can build it into your continuous integration systems, as a number of people do, or you can just use it running on desktop as part of your IDEs. But it also helps catch regressions in code before said code hits production, which is one of the issues that people often run into. So one interesting anecdote there, Marks and Spencer's had a fairly major data breach a little while back. Basically, they introduced a regression into their system as a result of a bug fix for some other issues, and were presenting people's credit card information to other customers. So I log in as me, and I receive credit card information in my view from other customers. Thankfully, it was only small parts of the credit card information, but it was still a fairly damaging story for them. And if they'd had proper static analysis and regression testing and so on and so forth, then this may not have happened necessarily. So, actually, we use it for code, we know about that. Can we also use it to analyze infrastructure? So, a lot of the modern systems for doing infrastructure as code are essentially just more software in some fashion or other. It's more source code. I'm sure a lot of you are familiar with infrastructure as code as a concept, but just for those who aren't, we're looking at systems definitions stored in configuration files of one form or another, being pushed and pulled by agents or servers, and some of the names down there will no doubt be familiar to quite a few people here. So often, if we want to test this, it's being tested with a number of different unit and integration testing tools. I understand Continuum are here today. BDD Security is one of the ones we see used quite a lot. There are a number of others as well. The idea here being that you spin up your environment using your configuration files, and what that gets us is a full environment we can test. We have some definitions of what this environment should look like. We validate that our configuration management tools have correctly set up the environment as it is expected. Now that's great. You've got to spin up a big infrastructure in the case of some organizations. You might be looking at hundreds of virtual machines, and that can get quite time-consuming and expensive potentially. So what else can we do? Some people are already looking at this from a point of view of maintainability, syntax, style checking, so on and so forth. There's a number of tools there. But we can actually also use this to catch security issues in the code bases for these tools as they're being pushed to your repositories. So as a few examples of the kind of things that would be pretty easy to find quite quickly, things like hard-coded passwords. I'm most familiar with Ansible personally. So the example here, Ansible has Ansible Vault. If you're just embedding your passwords in plain text in your config files and those are being pushed to Git, that's probably not a great thing to be doing. So flagging issues like that is great. Presence of unnecessary tooling on servers. So often if you're building a server, you'll need GCC and the rest of the build tools, but you might not necessarily need them on the production server once that's finished. Now, as a penetration tester, if I get onto a box and I've got GCC and a whole load of interpreters for languages you're not using and so on and so forth, that makes my life an awful lot easier because rather than having to set up cross-compilation tool chains and things, I can just compile on the server. So removing things like that is also worth noting, and you can pick that up too. Or equally, just failure to apply some of the common hardening principles you see people applying. SSH configuration issues, password authentication or root login, overly permissive firewall rules. Maybe they're not applying the kernel hardening that's you're expecting them to use, and things that your policies are defining must be in place. We can catch a fair number of them probably before it even actually hits the repository. What do we actually need for doing that? Parser for the configuration management tools domain-specific language. Often that's quite easy because there'll be either a programming language themselves, in the case of a few, I know Ruby's quite a common one, or YAML in the case of Ansible, and they're all established languages, very easy to find existing open source libraries to parse for you. And you need some kind of rules engine, essentially a list of rules that define what you expect good to look like or what you expect bad to look like, such that the tool has some idea of what it's looking for. To analyze, as we discussed before, walk the AST that you've created, compare the tree nodes against your rules database. This actually, in many respects, is much easier than source code analysis because what is happening in these tools is less complex than a full programming language, and so you don't need taint analysis. You don't need your pointer tracking. There's no pointers in any configuration management systems that I come across, and so building this is much easier in many respects than building a full source code static analysis tool. As an example, let's take a look at some Ansible. Here we're setting up or enabling UFW on a box, and we're allowing some password authentication through SSH. First one's probably pretty good, second one not so much. So we have some rules that catch these kinds of cases. We look for password authentication. We say if password authentication is yes, then we should probably raise that as an issue. And likewise, if UFW is set with its default policy as allow, that's also not great. And so we run this over the static analysis. The configuration files we defined, and so here we flagged that we found a rule involving a task involving UFW. Our rule catches that. It then checks what the policy is and sees that the policy is set to deny. That's fine, everything's okay. We now flag that we've got a line in file entry our previous rule if we check. So we find a line in file, we then look at the regular expression that defines the line in file rule, and then see what happens with that. So here we find that the regular expression contains this password authentication thing, which is what we're looking for, and we then check what the contents of it is, and lo and behold, someone's decided that password authentication on SSH is great and they don't like keys. So that is something that you can then flag and get fixed. Now, why does this help relative to the usual testing methodologies for infrastructure? You can enforce common good practices in an environment agnostic manner. If you've got a number of different environments across your enterprise, often the BDD suites and so on and so forth have to be customized a reasonable amount for each environment you're running it for. This is environment agnostic. It raises the number of false positives potentially relative to BDD. You don't have as good an understanding of each environment, but again, it means that you've got a couple of people that can write this and it can be spread out across your entire organization. And it complements it. You're catching issues at a different stage in your development process. As I say, it can be run locally on a developer's machine. That might not be an issue for some people. If you're only spinning up 3 or 4 VMs, then doing that within Vagrant is pretty easy. But if you've got a large infrastructure and you need to spin up 50 machines in order to get everything working, that might be more of a concern. And it complements the automated integration testing, as I say. So, to conclude, all this kind of thing can catch quite a few classes of bugs cheaply. You're never going to replace penetration testers, unfortunately. Well, good for me, I'll still have a job. But you can catch an awful lot of things quite cheaply comparatively by using these tools. You can build it into your continuous integration systems to get the automated security that brings for it. And actually, you can do this with infrastructure as well as source code as is traditionally done. So thankfully, we're actually finishing early, so everyone can go get a beer. But in the meantime, do I have any questions? I guess everyone just wants the beer then. Fantastic. Thanks, guys.